Hello everyone, in the following video we're going to talk about primitives, specifically primitives in Java. A primitive is the most basic data type in Java. It stores simple values. When we're talking about primitives, we're basically talking about one of 8 different things in Java, right? These are our data types. So remember that Java is a strictly typed language, which means that when we are creating variables or when we are making methods, we're making our compiler a promise, right? And that promise is that, this container is going to hold a specific type of value in variable creation, or this method is going to give us back a certain type of value in method creation. And our compiler holds us to our word, right? It make sure that we do what we said we were going to do, or we give it what we said we were going to give it when we declare these data types as part of our declaration process. And so these are simple values rather than objects, right? Because when I look at the list of the 8 different data types, there is a data type that we often consider that is not on that list, and that is string. A string is a data type in Java, but it is not a primitive data type, because a string is an object of the string class in Java. And when we look at our data types here, one of the data types that we'll talk about, and it may as well be the first data type that we talk about, which is a char. A char is a singular character. And we typically define that in variable creation with single quotes. And so what we're looking at when we're looking at a char is a single ASCII character, and we bring this up now, after our discussion of kind of why a string isn't a primitive, because a string is just a bunch of chars that have been kind of strung together. Right? Remember that characters, that words in general don't really have any meaning to a program, right? Or to our computer. It's looking at specific characters and it's comparing them against the ASCII chart to get the pattern of ones and zeros of binary that makes up this character. And so words really mean nothing to my computer, but characters do. Right? A character takes up 16 bits of memory in our program. Right? So just one thing to kind of think through as we're going through this is that it is 8 bits in a byte. Right? So when we're saying 16 bits here, we're thinking 2 bytes of memory. So when we are creating a container that's going to hold a char or a character, we're creating a container that's going to hold 2 bytes of memory. We're reserving 2 bytes of memory in our program to hold this character. And this can be any keyboard character, this can be numerical, this can be symbolic, like it can be a symbol, or letters, lowercase and uppercase. It can be any character basically that's on the ASCII chart. And so that's the first of our 8 primitives that I want to talk about. The next one is going to be a byte. And a byte's just going to be something that takes up 1 byte of memory, right? So it's going to be 8 bits. And in this case, it's going to be some number, right? It's some whole number between -128 and +127, right? So for the purposes of this little code demo here, let's say it's 114. And so the big thing that we take away from this is that it is, in fact, 8 bits, right? 8 bits in a byte, 1 byte. So when we're creating this, we're reserving 1 byte of memory for this. Now, as we said, right, this can only contain numbers between -128 and +127. because these are the amount of, these are the integers that can be represented within 1 byte of memory, right? Like if you remember back to your discussions on binary, right? We look at our binary place values, 1, 2, 4, 18, 6, or 1, 2, 4, 8, 16, 32, 64, 128, right? In a singular binary octet, or 1 byte, we have places 1 to 128, and we can represent numbers, we can represent 256 numbers with these 8 bits in memory, right? And if we look at our range here, what we see is 256 numbers that are being represented, right? Negative 128 to 127, zeros in the middle there. So these are the numbers that can be represented in 1 byte of memory. Now these are rarely used, right? Because in modern computing, oftentimes our computers have a lot of storage and a lot of memory. And in those cases, we don't really worry as much about memory conservation. But if you're looking at something like a microcontroller or something like a more closed-off, memory-constrained environment, where every bit, every byte counts, right? Using a byte or using a short could be really, really significant in terms of helping you manage memory, right? So you're only using the memory that you're needing, and you're not reserving memory in the event that you have a bigger number, because you know that your number is always going to fall within this realm that can be represented within 1 byte. And so the next one is a short, which falls along those same lines. A short is like a byte, but it's a little bit bigger, right? A short represents 16 bits of memory, or 2 bytes, right? And that expands us in terms of what we can do with the value here. It's a little bit more than it can hold, right? So this is going to range from negative 32,768 to positive 32,767, right? So it's going to be that 65,000-ish values right in there, right? Because we have that extra byte. We have that extra octet of memory that we don't have in our byte primitive. So this could represent something like a 12,432. Right, so this takes up 16 bits of memory, and it runs from negative 32,768 to positive 32,767. The next one on our list is the standard int, and this is the one that you'd see used most often. It is not comprehensive, right? This is not all values, right? This is a 32-bit integer. So it's what can be held within 4 bytes of memory. So that's going to range between negative 2,147,483,648 to positive 2,147,483,647. For the sake of space here, I'm not going to add it to my comment at the end here. But this is the one that's going to fit most use cases, right? Like it's going to be the most efficient memory-wise while still holding a ton of numbers, right? Like we're looking at nearly 5 billion values that this could hold within that 4 bytes of memory. So this could hold anything in that value range. It's reserving 4 bytes of memory, so it could be 1 million 230,000, 1,230,467. Right, and again, that is being stored within 32 bits. Or 4 bytes of memory. The next one we see is our long, and our long is our integer variable value that can hold the widest range of values. Right? It can hold values between negative 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854 million, 765,808, and positive 9 quintillion, 223 quadrillion, 372 trillion, 36 billion, 854 million, 775,807. Right, so absolutely huge numbers here. But to put this in a bit of interesting perspective, right? This only requires another 32 bits on top of an integer, or on top of an int, to store all these values, right? So this is 8 bytes of memory that can store this value. So let's say we're going 1,234,567,890,123. And that's going to be our long value. Right? And that's stored within 64 bits of memory. We're reserving 64 bits of memory. So now hopefully you can kind of see how this memory conservation sort of works here. Right? Like if I know my value is always going to fall within a byte range here, I can save myself 56 bits of memory if I use a byte instead of a long. 24 bits of memory if I use a byte instead of an int. Right, so carefully choosing your data type that you're going to use is significant. Definitely can be significant depending on the environment. One of the things that we kind of say a lot when we're working through class is that on your system, you control the environment in which your program is run on your system. You can't necessarily control the environment that it's ran on outside once you release it into the wild. Right? So this gets into big concepts of efficiency. When we talk about things like big O notation, which we might do in a future video. What's the space complexity of this program? And as we're adding more memory to our program and the stack is taking up more room in memory, it may bog down computers with lower specifications, right? Microcontrollers, or things like Raspberry Pis, right? If we're putting something out in the wild that's designed to do a specific thing that has a real memory constraint in terms of what it's able to use to run your program, you have to be really conscientious of which data type that you use. Although if you're using a modern computer otherwise, you can kind of just use an int for everything unless you're, using some really big number, and you'll be fine. Now, one of the things that we do see from all four of these primitives is a lack of precision, right? And that's where our floating point numbers come in, right? There are two types of floating point numbers. There is a float, which is a single precise number or a single precision floating point number or decimal number. This takes up 32 bits of memory. It is less precise than a double, which is our other one. We could say this is something like 3.14. Right? And this takes up 32 bits of memory. Whereas a double is double precise, right? That's where we get the idea of double. So it's going to require more memory in double precision. We're looking to about 15 decimal places. Right? So, if we were to say our floating point value here is 3.14, our double value would probably be something like 3.1415926535897993. Right? So let's type that into our program here. 3.1415926535897993. So this is going to be 64 bits of memory, and it's double precision, up to 15 places. And so these are 7 of our 8 primitives. The final one that we want to look at is our Boolean value. And in terms of memory, from a practical standpoint, right? Or maybe more so from a theoretical standpoint, Boolean takes up 1 bit, right? Because it's basically one item in our binary, right? It's just a 1 or a 0, it's an on or an off, it's a true or a false, right? So our Boolean values are always going to hold true or false. And that's going to kind of represent 1 bit of memory. Now, the actual space a Boolean can take up in memory kind of varies, right? It's going to depend on the implementation. Whether you're using it, on its own like this in sort of a flag variable, or you're using it, as a part of a conditional statement or as a part of a loop, right? The application is really going to depend on how much space that Boolean is going to kind of take up. But it's going to be generally considered 1 bit of memory, a true or a false, and a whole idea from the Boolean primitive and the idea of binary in general, all that kind of goes back to a guy named George Boole. Right? George Boole was a mathematician, philosopher. He's from England. We're talking early 1800s here, early to mid 1800s, I believe. And he basically postulated that every mathematical equation can be solved through a series of trues and falses. And that's kind of the foundation, the basis of what computing is based on, right? The idea that every mathematical equation can be solved through a series of trues and falses, right? Because what is binary but trues and falses, ones and zeros, right? It's either on or it's off. And so if we string enough of those together, then we end up with a pattern that our computer can recognize and use to do math. And we can look at things like bitwise operations and things of that nature, which we don't really get into in this area, but it is pretty useful for computer science that utilizes the binary to do the calculation. So these are our 8 primitive data types in Java. Remember that string is not a primitive data type. It is an object of the string class. So these are our most basic representations of values in Java. You'll see them in basically every single program that exists. And so that is all that I have for you for this video. Thank you for watching.